Hello everyone. The title of this presentation is an overview of the role of solid-state transformer in grid-connected wind farms. This presentation is based on the following outline: 1. Introduction. 2. Functional and structural overview of solid-state transformer. 3. Conventional wind farms based on STATCOM. 4. Modern wind farms based on solid-state transformer. 5. The roles of solid-state transformer in modern wind farms. And 6. Conclusion. Introduction. Traditional wind farms often make use of line frequency transformer, static synchronous compensator, that is STATCOM, and power factor correction devices for grid integration of wind farms. However, such components are usually bulky, makes a lot of noise, and causes greenhouse emission. The bulky power transformer for both STATCOM and wind farm generators hinders this configuration from applications where volume and weight are critical issues. Based on this, STATCOM interfaced wind farm cannot be sited where size, weight, compactness, cable solution, multi-port capability, and environmental friendliness are critical issues. This paper demonstrates how solid-state transformer replaces the STATCOM, the bulky transformer, and the additional reactive power compensation devices in grid integration of wind farms, thereby providing smaller footprint, compactness, and high performance. Functional and structural overview of solid-state transformer. Figure 1 shows the structural diagram of solid-state transformer used in wind energy conversion system. As we can see, the solid-state transformer consists of 3 power converters, namely an AC-DC converter that regulates the high voltage direct current, which is HVDC link, a DC-DC converter, typically dual active bridge converter, that regulates low voltage DC current, that is LVDC link, and of course a third converter known as DC-AC inverter that produces a regulated low voltage AC bus. Conventional wind farms based on STATCOM. The techniques used for wind energy conversion system reported in literature are categorized based on the type of generator used. The most common ones are the squirrel cage induction generator SCIG, the doubly fed induction generator DFIG, and the directly driven synchronous generator DDSG. The technique based on squirrel cage induction generator is shown in Figure 2. The excitation of the squirrel cage induction generator is provided by the high voltage grid. The major features of this configuration include direct connection with the grid, constant rotational speed, provision of substators for smooth connection to the voltage grid, and provision of capacitor bank for reactive power compensation. The technique based on double-fed induction generator is shown in Figure 3. The major features of this configuration include direct and sub-connection of the generator with the grid, as well as the provision of power electronic converters for speed control and reactive power compensation. The technique based on direct driving synchronous generator is shown in Figure 4. The major features of this configuration is the use of full power back-to-back power electronic converter in decoupling the generator completely from the high voltage grid. Modern wind farms based on solid-state transformer. In order to ensure smooth and efficient grid integration of wind farms, the solid-state transformer technology is employed to replace the STATCOM, the bulky transformer, and the reactive power compensation devices used in the conventional wind farms shown in the previous slides. Figure 5 through 7 show the functional diagram of solid-state transformer in modern wind farms. Figure 5 is a block diagram of solid-state transformer based wind farm with squirrel cage induction generator, where the solid-state transformer replaces the STATCOM. The two transformers and the capacitor bank used for active power compensation, thereby providing smaller footprint, compactness, and high performance. Figure 6 shows the block diagram of a solid-state transformer-based wind farm with doubly fed induction generator. In this configuration, the partial back-to-back AC to AC converter is retained, whereas the SST replaces the STATCOM and the two transformers. Figure 7, on the other hand, is a block diagram of solid-state transformer-based wind farm with directly driving synchronous generator, where the solid-state transformer replaces the STATCOM, the two transformers, and the full power back-to-back AC-AC converter. Roles of solid-state transformer in grid-connected wind farms. Solid-state transformer provide direct interface of the wind farm to the power grid, while realizing the task of voltage isolation and voltage adaptation. It provides smaller footprint, compactness, high performance, fault tolerance, and improved power quality. Solid-state transformer can effectively suppress the voltage fluctuation caused by transient nature of wind energy without additional reactive power compensators, and as such may enable large penetration of wind power into the grid without any problem. It offers integrated functionalities of power management, fault management, and energy management. Solid-state transformer function as circuit breaker, in which case the power electronics used in the SST are turned off. Once such power electronic components are turned off, the flow of electricity will stop and the circuit is interrupted. As such, SST behaves as circuit breaker in that case. Solid-state transformer employs a high-frequency transformer whose size is inversely proportional to its frequency. Hence, a higher frequency results in smaller transformer with 80% lesser volume. The high-frequency transformer used in solid-state transformer doesn't need any transformer oil, as such guaranteeing safety from that perspective. Solid-state transformer has much smarter protection approach compared to line frequency transformer, which make it able to effectively isolate load and grid-side transient, including load short circuit condition and unbalanced input voltages, among others. As such, it increases the power quality of the system. Solid-state transformer guarantees seamless fault-right through operation during both symmetrical and unsymmetrical fault as per the latest grid codes. It provides instantaneous voltage and current regulation because of the solid-state devices and switches, active power transfer, reactive power combination capability, and voltage conversion functions, and a lot more. It also has DC port for easy integration of other renewable energy resources and DC microgrid. It has low electromagnetic compatibility concern and is equipped with fault current management capability on low voltage and high voltage side. Conclusion. Solid-state transformer has been identified as a potential alternative that can be used to achieve smooth and efficient integration of renewable energy resources with the grid. This paper has covered the roles of solid-state transformer in grid-connected wind farms. It has been demonstrated in the paper that solid-state transformer can replace STATCOM, the two transformers, and additional reactive power compensation devices used in grid integration of wind farms, thereby providing smaller footprint, compactness, and high performance. It is therefore concluded that solid-state transformer interface wind farms can be sited anywhere because of the reduced size and weight, compactness, cable solution, multiple capability, and environmental friendliness. These are some of the references used. Thank you for your time.